Thank you very much for introduction, and I thank organizers for kind invitation. Continuing today's discussions, I would like to go slightly bit further towards anisotropic setting, namely crystalline elastic flow. So in this setting, we have yesterday and a day before yesterday, we have seen very interesting talks related to anisotropic perimeter, anisotropic curvature, and so on. And today I would like to discuss more extreme case where anisotropy is not smooth, not elliptic. So basically, it is its wall shape, its unit wall is polygonal. And so what is anisotropy? So as we know, so this is positively one homogeneous. So I'm not assuming evenness. Positively one homogeneous convex function, and I denote by W phi, so wall shape of phi. Yesterday's talks we have seen that wall shape is defined with respect to dual norm, dual anisotropy. I'm taking unit wall as a wall shape because my perimeter, let's say length, anisotropic length, will be defined with respect to phi dot. And that's why its dual, its wall shape will be basically phi dot dot less or equal 1. And since phi is convex, so this double dot eat each other, and I end up with this formula. And so crystalline means this set is basically convex polygon containing the origin in its interior. And this kind of things, starting from the seminal works of Taylor, studied a lot, especially related to anisotropic crystalline curvature flow. And so basically, when phi is smooth, let's say phi is Euclidean, how the curvature enters, it is just first variation of the perimeter. So when I differentiate, I slightly perturb my curve, and then I differentiate, and I end up the curvature here times nu. So I end up curvature here, and the same happens when I use anisotropy. So curvature is second derivative, basically divergence of unit normal. When I have anisotropy here, then instead of normal, my curvature changes slightly with respect to so-called Kahn-Hoffman vector field. So this is defined as a gradient phi dot times nu, supposing, for instance, phi dot is elliptic, smooth, and so on. An important thing is here I can compute when it's elliptic, its gradient. And then I take, not divergence, so this is tangential divergence. I can take tangential divergence to define anisotropic curvature. So in case of this anisotropic perimeter, I end up with k phi nu times x dh1. And in this situation, in crystalline situation, still I can define curvature in this formula. But now, instead of gradient, I have to put subgradient, unfortunately. And now, because of these corners, it is a set. And to take divergence, I have to choose vector field from this subdifferential. And this should be smooth enough so that I can compute its divergence. And this means I have several curvatures, and so my problem seems not very well posed. And to make it more well posed, what I do is basically I take all possible this kind of vector fields, Kahn-Hoffman vector fields, which admits divergence. Let's say they are Lipschitz Kahn-Hoffmans, and then I take integral, I take square, I take integral, I compute the sort of length, and then I minimize with respect to this Kaufman vector fields. When I compute this minimum problem, I end up some minimum Kaufman. Let's denote it by n0. And in the polygonal case, it turns out this, supposing that my gamma is polygonal, and it admits this kind of Kaufman vector field, at least one Kaufman vector field, it turns out that this n0 is nothing but the, so supposing that this is my curve, this minimal Kaufman turns out that nothing but, so here at the corners of the curve, it is uniquely defined, and it is linearly interpolated between inside the segment. And this means if I compute its divergence is constant, because this is linear interpolation. And so if I introduce a sort of velocity equal to curvature, so this curvature is with respect to divergence of minimal Kaufman, and we can show that divergence is unique because it is strictly elliptic, so convex, because there is a square. So the minimizer of this, if exists, has unique divergence. And this divergence, I say, curvature of the curve at this point. And so this observation related to polygonal curves implies that on the segments, my curvature is defined constantly. And if I write the usual, maybe minus here, depending on how I define velocity, if I define mean curvature flow regarding to this polygon, then curvature of each segment is constant. So morally, segments are translating. And I am translating to new polygon. Okay, I am cheating here a bit, but this guy doesn't move. But okay, so this guy is translating in the normal direction. So my curve, I can orient my curve such a way that it's normal, let's say, going outside. And so each time, according to this flow, my segments translate always in the direction of the normal, maybe up, maybe down. So I can always define this notion called sinus height from the segment SI0 to SI times normal. And this is positive if I move according to the normal direction, otherwise it's negative. And this HI is giving sort of how much I am translating. And it is derivative, basically gives me velocity of the translation. And so my equation, so mean curvature equation in this setting becomes just ODE for the system of these segments. And so for each time, I have to compute H prime equal to K phi. Now I have one small problem, and which kind of polygons I can find at least one Kaufman vector field. If I find one Kaufman vector field, so this means it is phi regular, and so this means I can minimize always this energy. And this brings me to the next slide. So I am considering here bounded, but we can consider unbounded curves as well with two half lines, segments always finite. And I say a polygonal curve is admissible provided that for each adjacent segments, let's say, for each adjacent segments, this and this, for example, I can find adjacent segments of wool shape, which has the same normals. Here on the left, this unfortunately not admissible, even though it's very beautiful and it looks like very parallel to this, because if I orient it in this way, to the clockwise, unfortunately, this normal does not exist in my wool shape. Converse, if I orientate in the other way, and this segment will produce the same issue. This means this is not admissible. Unfortunately, I cannot consider here in this talk such kind of singular sets. It is sort of singular for my wool shape. But this is very nice. So this is minimal, sort of minimal Kaufman, and the corners, the vectors are very well defined. And so this is admissible in my situation. I'm not assuming it's embedded. I can consider embedded or non-embedded, so it has self-intersections, immersed, and so on. And as I said, minimal curvature, minimal Kaufman vector field is always linear. So this means each of my segment has constant mean curvature, and I can compute it explicitly using this divergence. And so it will give me 0 if SI is half-line. Basically, when SI is half-line, I can extend my Kaufman constantly as soon as it is uniquely defined. I can extend it constantly along this half-line. And so here divergence is 0, and at the end, I end up curvature 0. If it is a segment, then it is just difference quotient of corresponding segment of the whole shape. So you remember this corresponding segment divided by the length of the segment. And then I have to multiply so-called transition numbers. These transition numbers means I am transiting from I minus 1 to I in the convex way, then this will be 1. If it is concave, then it is 1, so I'm minus 1. So if I'm going a bit concave, and if it's neither convex nor concave, then it is simply 0. So in mean curvature evolution, these segments doesn't move. So morally, my evolution just like this. These parts are becoming smaller, but this segment stays still because its curvature is 0, and by this formula, it has 0 velocity. It doesn't translate. And now I defined what is curvature, and according to what Miura-san said, I can introduce elastic energy, and in this case, crystalline elastic energy. In the same way, I add length and then curvature square. And since I can have unbounded curves, I can localize it for some bounded open set, or I can completely compute the energy. It could be infinite in the unbounded case. Clearly, when alpha equal to 0, this is just nothing but the length. And we have already seen this slide, so I apologize for repetition. So this is in the case of Euclidean anisotropy. So elastic energy is defined 1 plus alpha k square. So here I'm following mostly to papers of Mantegazza, Pozzetta, Bellettini, Mantegazza and Novaga, and also Garke, Pluda, and Menzel, if I'm not mistaken, Menzel, and so on. So here I have 1. So this is slightly different from the first talk of Anne. Here, I think she assumed k square. And if you compute the first variation of this energy, so this k is coming from the 1, from the area, and then this terrible term related to the first variation of k square, Wilmore energy. And accordingly, gradient flow is defined following this system of PDEs. And this very complicated system. So here, first order system is already explained. No comparison principle, no preservation of nice things like convexity or embeddedness or these kind of things expected. However, as it said, evolution starting from closed curve always exists, and it always stays in the compact region, never escapes to infinity. And as time goes to plus infinity, flow stays in the compact region and ascent converges to some stationary solution. And several results also known, as I said, in the papers, for example, Garke, Pluda, and Menzel, in the case of networks. And also unbounded curves, now Miura-san explained. Following this, I consider first variation of F alpha, my elastic energy. Now I have to define what kind of perturbations I consider. Because in the smooth case, I can always consider smooth perturbations, but here I should be a bit careful. And how do I perturb? For example, I have the piece, part of the curve. I could allow facet breaking, or as in the case of crystalline curvature flow, I don't allow facet breaking. Here, in this talk, I don't allow facet breaking. Basically, I don't know what happens if you allow this facet breaking. I know some people like Giga, if I'm not mistaken, deal with this kind of situation. But here we confine, as in the case of crystalline curvature flow, and let's see if you can retrieve the results in the case of Euclidean anisotropy. For example, this global time existence or convergence to stationary solutions and so on. And my first variation is an admissible. I say, okay, my segments translate parallelly as in the case of this crystalline curvature. And then if I estimate the first variation, I end up with something like this very long formula. So this is related to first variation of the anisotropic length. And this is related to first variation of the curvature, crystalline curvature. As you see, my perturbation, slight perturbation, involves both I-1 and I segments. So naturally, in the expression, you see curvature of I-1, curvature of I, and curvature of I+1. Basically, as Professor Chambol explains, this is sort of second derivative of the curvature. So I-1, I, and I+1. It's sort of. And so this is my first variation. And accordingly, I define my flow exactly velocity. So this is time velocity, if you remember. And this time velocity equal to minus first variation of my energy. And here I put some strange weight. This is usually done in order to have wool shapes evolve self-similarly. And so I say, okay, so first of all, gamma T is crystalline elastic flow, starting from admissible polygon. First of all, they should evolve parallel to initial gamma 0, and segments, for each segment, the sinusoids, which I introduced earlier, satisfy this ODA, and they are sufficiently regular. And then we will see this. You will be immediately see infinity. So this is my evolution equation, evolution system, and this should hold in the case of half-lines for all segments, because I know that these guys do not move. I'm assuming this is sort of directly boundary condition. And we can check that if I have crystalline elastic flow, then the derivative of my energy is negative. So this is minus h prime square. I think this is exactly what Miura-san said. So my energy is decreasing. So here, I didn't write this f gamma t equal f gamma 0 minus integral, but for me, this is also more important. Here, what I am seeing is during the evolution, my segments, supposing that my curve is bounded, during the evolution, my segments do not become very large. So it always stays finite. And also, during the evolution, if my CI, so transition coefficient, is non-zero, in other words, segments with non-zero curvature always remains bounded away from zero. So the length of non-zero curvature segments always stays non-zero and finite. But with zero curvature, we don't know because they are not included in the energy. They included somehow, but they are not counted. And then let's consider some small examples. In the case of wool shapes, let's say I'm considering some wool shapes evolving crystalline elastic flow, and in this case, I can explicitly compute curvature like this, and velocity, I mean this sinus distance, is exactly like this. And here you see this weight which is coming in the denominator of the velocity path. And if I put it here, then what I get is this formula. If I put inside my equation, and this very long sum seems nothing but the transition coefficient multiplied by the corresponding length of the wool shape. And if I compute this divided by this, I exactly end up this equation, which is, I imagine it is the same for Euclidean elastic case. And this means my evolution is self-similar. If I solve this equation, if I solve this ODE, my evolution will be self-similar. And one interesting observation is, if my radius is square root of alpha, then evolution stays stationary. It doesn't move. It always stays the same. But if my radius is slightly bigger than alpha, the square root of alpha, then my evolution is decreasing. So radius, so my wool shapes are decreasing self-similarly to this stationary solution of radius square root of alpha. The converse also holds. If my radius is strictly less than alpha, then evolution increases, and I again converge to this wool shape of radius square root of alpha, which is stationary. And important thing is here, time is always infinite for all these scenarios. Another interesting observation is related to Grimm-Reaper type evolution. So this is sort of translations. Suppose that my wool shape is this, and I consider evolution starting unbounded curve of this form. So here the angle is theta. Sorry. Here the angle is theta 2 and theta 3, exactly like this, let's say, so that cotangents is this, both guys are positive. In this situation, the only evolving segment is S2, and these are half lines like directly boundary conditions. And this means my H2, so second segment, so this segment is translating to the infinity. So it's escaping to infinity. On the other hand, suppose that my half lines intersect. In this case, my cotangents, both of them are negative, and so I get positive sign here, and I can compute the spatial definite length of S0, for which the flow is stationary, it doesn't move. And if I'm slightly perturbing, then the flow exists for all times, and in the limit, it is converging to that stationary solution. So in this situation, I don't go escape to infinity, rather I converge to stationary solution at the maximal time. And so this is giving some hints. So my flow could exist for all times, and at the maximal time, I converge to some stationary solution. And let us discuss the first issue, existence. Unfortunately, we cannot immediately say that the flow exists for all times, but we can say that it exists up to some maximal time, T-DAC. It could be infinite, of course, or it could be finite. And the flow has semi-group property because of uniqueness. As in the case of Euclidean elastic flow, we have also uniqueness. And it has semi-group property. If I start from 0 and if I start from time t, then this starting from time t is continuation of the flow starting from 0. And also, supposing that initial curve is bounded, and supposing that I have a singularity at maximal time, then the flow is Kuratowski continuous, and it is always remains bounded. It never escapes to infinity. And also there is an index with this property. The length goes to 0. And I know from energy estimates, only place where length could go to 0 is the segments with 0 curvature. So in the flow, what I get is, so if this is my flow, in the flow I can get something like this. This is converging to here, this is converging to here, this is oscillating a little bit, but at the end, this segment is disappearing. An interesting thing is after disappearance, my segment, my polygon, still remains admissible, still admits the same Canofan vector field, same stuff. I can compute curvature and so on. So even if some segments with zero curvature disappear, I end up with polygon which is admissible. So this means I can restart of the flow starting from the singular polygon. And even if singular for the previous flow, it will be non-singular for the new flow. So I can apply the same existence result again and again, and at the end, I reach to infinite times. So this means I can finitely restart my flow, and for each these intervals, for each interval between consecutive segments, it is exactly the unique maximal elastic flow, and the flow is always Kuratowski continuous, even though some segments are disappearing. So as you see, flow is continuous basically in the sense of Kuratowski. I'm not jumping, I'm not shrinking suddenly, and so. And also at each time, one segment or more segments with zero curvature stays disappears, or other non-zero curvature segments always stays and length stays bounded away. And important thing here is the index, the number of, let's say, loops, signed loops, always remains constant. It is always equal to the index of the gamma zero, because destroying zero length zero curvature segment does not change the number of loops. So this means if I start with something like this, suppose that I have a loop, and if I destroy this one, the number of loops doesn't change. So loops is still the same too. And now this solves my issue, so I can define my flow, not in the very beautiful way, okay, with restarts, but up to maximal time, infinity times. And then I come to second question related to what happens as time goes to plus infinity, and what is behavior of my flow, at least in the case of bounded curves. In this situation, I would like to follow these arguments as already mentioned. I want to prove that it converges to stationary solutions. And stationarity means first variation is zero, so for all segments, this quantity should be zero. For instance, in the case of square norm, so quadratic norm, square norm, so in the case of this, maximum of module x1, module x2, these two guys are stationary. Here, this is one parameter family, A. So if I change this length up to certain amount, the stationarity doesn't change. It always remains stationary. But segments with non-zero curvature always should have the same length. I cannot change this length if I want to keep parallels, but I can move this vertical segment up and down a bit. And here, unbounded case. Here also, length of this quadrat square I cannot change. Length of this slightly longer segment I cannot change, but I can change this vertical segment. I can go down to infinity, so I can translate two parts apart. And let me do, for example, more complete analysis in the case of square norm. In this case, my first variation simplifies, and cosine term disappear. Cotangent term disappear, and I only get a sinus term, which is either 1 or minus 1. So because my angles now, admissible curves, always are rectangular, so it should be always of this form, maybe self-intersections, but they're always rectangular form, so angles are always either 90 degrees or 270 degrees. And so, in this situation, we can completely classify how stationary curves look like. Unbounded case, we have only 3 possibilities. One possibility is there are no loops, there are no squares or rectangles. It is just sort of monotone function. It is step function. It could be also a number of squares joined by zero length curvature, zero curvature segments. 1, 2, for example, here, 3 here, 4 square here, and so on. You can put as much square as you wish. And another one is double right angle chain. So this means I have to fix these two sides of the chain. And this is completely known. It's square root of 2 alpha. And A and B are, they satisfy inverse Pythagorean equality. So this means if I choose any A and B satisfying this condition, then my stationary curve looks like this. So this is one chain. Here two chains, these guys. And here 3 and 4 and 5, 6, and so on. You can put as much this kind of object as you want. But you always connect with 0 curvature segment. So this is in the case of unbounded case. So if you find some sort of stationary curves, then it should be one of them. In the case of, in the case of compactness, in the case of boundedness, the situation is slightly different. So this is figure 8. Now I have, again, 3 possibilities. I have figure 8 and several figure 8s. As you see, I can put as much square, even number of square of side length square root of 2 alpha as I wish. And all of these guys has index 0. This is sort of square root, figure 8s, figure 8s, figure 8s. And the same figure 8s with rectangles. So rectangle has, as I said in the one of the previous slides, it has definite length, square root of 2 alpha and square root of 4 alpha. And I can put as much square as I wish. So 2, 2, here 4, 4, and so on. So this is another form of stationary curves. Here we have some structure. You see the number of this kind of objects, rectangles or squares, they should be always even. So this is always figure 8 type. There is no half figure 8, unfortunately, here. And the famous wool shape, and it's several covers, as Anna mentioned. It's not only just from outside we see here just one, but it could be several times loops along this square. And it only possible non-zero index could have this wool shape. And now we have luckily Lojasiewicz-Simon type inequality. Here it is version of Lojasiewicz-Simon, and how it looks like. So it is exactly a difference of energies. And if my curve is close enough, so this gamma is closeness estimate. If my curve gamma is close enough to my stationary curve, polygonal curve, then I can estimate the difference with first variation of my energy. And this is the main ingredient in the, I think, so we can always pass to the subsequence. Up to the subsequence, it converts to stationary solution, up to subsequence plus up to translations. But if you want to do it without translation and without subsequence, and unfortunately, only thing to the best of my knowledge, only thing you know is you should have this kind of estimate. And luckily here we managed to obtain this estimate. And because of this, thanks to this, we can say, okay, what happens in the long time? First, let me assume that this length does not vanish after certain time. So I restart my flow after certain time. I don't need any more restart, and flow always continues. And no lengths disappear after that time. Then this Lojasiewicz-Simon implies that there exists stationary polygonal curve parallel to gamma t, so initial this time, such that gamma t, as time converges to plus infinity, converges to this stationary curve in the sense of Krotowski. Here, unfortunately, we cannot say C infinity and so on. Maybe we can say, but here is more seen with this Krotowski convergence. And also, what we can say that we can say a bit more, supposing that this will be 0 at infinite time. So this A0 is 0 at infinite time. And in this situation, also the assertion stays true. But you have to extend the notion of stationarity if I drop this assumption. Up to now, I am very well aligned with Euclidean case. But unfortunately, my flow preserves convexity. And here is the main difference from the Euclidean case. And as you see, if I start with convex admissible polygonal curve, so convex means all Ci equal to 1. So it could have loops, but all Ci, so there are no zero segment curvatures. Zero curvature segments. In this case, flow exists for all times. And this is, apologies. Flow exists for all times, and in the limit, it's a maximal time, I converge to wool shape of square root of alpha. So you remember this is stationary wool shape. And now you could ask, okay, so this is different. What could be, why this problem is interesting? So one way to see this is what I know Wisken's theorem for curves. We know in 2 dimensions, Wisken showed, if I am not mistaken, if I start with some closed curve, then in the limit, it always becomes round, circle, and then disappears. And to the best of my knowledge, such things is not known in the case of crystalline case. We know, so it maximal time, some segment disappear, maybe it's zero curvature or non-zero, some segment disappear, but this kind of analysis, so first of all, extension after singularity appears. Second, what happens in the maximal time, this is not very much studied, and this was first attempt, so okay, we approximate curvature flow of Taylor using this singular perturbation of adding this curvature term, and we approximate this flow, and the flow is well aligned until, if you see the equation, if I take alpha equal to 0, I exactly end up with mean curvature flow for polygonal curves. And this is sort of perturbations which exist for all times. And let's see what happens as alpha converges to 0. This is sort of ongoing work. So we have to slightly arrange the things. And another thing is, suppose that I start, so this is one motivation. Another motivation is, suppose that now I would like to consider Euclidean ball, and I approximate it using polygons. And then I send number of polygons infinite, and at the end I end up with smooth Euclidean ball. And what happens in this situation, and to what converges my flow? So it is known that when alpha is equal to 0, my evolution equation converges to evolution equation, Euclidean mean curvature flow. But in this situation, do we converge if we send fixed alpha and if we send a wool shape to ball, do we converge to Euclidean elastic flow? As we see, it is no, but what is the limit of this flow? No, because I preserve convexity, so this is a bit, but still, so what could be limit flow? So these two are currently open directions which we are working, and also open directions are in the case of unbounded curves. So as Mura-san said, can we, for example, somehow study what happens in the long time if I start with unbounded curves, not like it's a maximal, not parallel lines, but also, as Professor Garke asked, maybe something slightly different, going up, going down, like this form. And what happens in this situation to the flow? So if I put some rectangles here, do I converge to stationary solution as in the case of bounded case? And these are all open directions currently we would like to consider. And I don't know how long it takes we reach until the final conclusion. And this is the end of my talk. Thank you very much.